I'm going to talk about reliable systems and how can they take advantage of heterogeneous cores, and I'm going to tell you that sometimes using slower cores is better than using fast cores. I've done this work jointly with Andy Tanenbaum, my supervisor, and Herbert boss. So the reliable systems we have in mind are so-called multi-server systems. They are systems based on a microkernel, which runs as the privileged code, and all the operating system functionality, which typically in systems like Windows or Linux is implemented by the privileged kernel, is, in our case, implemented as a collection of isolated processes in user space, which you call servers or device drivers. The advantage of this design is that if some of the system processes or server crashes, it doesn't necessarily mean that the whole operating system also goes down and everything stops. We can actually restart the component or even replace it with a component which has the problem fixed. And if we have a patch for the problem prior to the crash, it's a known bug, we can actually replace the component on the fly without disturbing the operating systems. The problem of this design is that the components, the servers, work on the request from the applications jointly, and each of them only works on a fraction of the request. That means that they have to switch on the CPU frequently, and that comes with lots of context switches, lots of overhead. Caches are not used efficiently. TLBs, branch predictors, are being thrashed all the time, which results in underutilization of the hardware and bad instruction per cycle ratio. So we started looking at how multi-core CPUs nowadays could help us to solve our problems. Now we have a bag of CPUs, and what can we do with them? So in our main design point is that we can dedicate some of the CPUs to some of the system servers. Not necessarily to all of the system servers, just to the ones that are important for the performance and specifically for the performance of the current workload. Another important change is that we're not using the microkernel interprocess communication anymore, but we use communication which is purely implemented in user space, which results in even thinner layer of the kernel running on the dedicated cores. And in fact, the kernel is completely avoided from the fast pass on these dedicated cores. The problem is that if we dedicate some of the cores, which we still have quite a few on the current architectures, they are missing somewhere else. We can't use them to run the rest of the operating system and especially the applications. So what we, also the cores are pretty big and they are designed for high performance of the applications. And if we dedicate these cores to our servers, they are heavily underutilized. So we started looking at whether we could benefit from different types of cores, what should these cores look like, and especially what should be the performance of these cores. The main architectures nowadays feature typically out-of-order deep pipelines, which is great for high instruction level parallelism, which some applications can take great advantage of. But researchers before us have already demonstrated that operating system code, due to its nature, because it's lots of conditional jumps, can take little advantage of these features, of the speculations and instruction reordering. And it takes no advantage of features like multimedia extensions and things used for scientific workloads or high-performance computing. So we have cores which are fast and relatively power-hungry, especially because they also power parts of the chip we can't really use in the operating system. Wouldn't it be better to use cores that have in-order shallow pipeline, which is great for to build a cores with many hardware threads, which is good for high throughput computing. And these cores typically run on lower clock speeds and they draw less power. The main advantage of these cores, in our opinion, is that they are real small and it can be fitted in much larger numbers on a single die. One good example of that is the recently released Xeon Phi by Intel, which has more than 60 cores and has 4 threads per each core. So what we envision is merging these big and little cores together, much like in the ARM's big little fashion. But in contrast, we think that there will be lots of small cores accompanied by only a few of these big ones for the performance of applications. Also, we do not rely on the fact that the instruction set is completely identical, but a large part of the instruction set is overlapping. We made a rough estimation based on the current chips. What could we expect from this merge? We take a quad-core Core i7, which uses 1.4 billion transistors, and a 62-core Xeon 5, which uses roughly 5 billion transistors. And we estimate how many cores of each kind we could fit on the 5 billion transistor die, which is presented in the table below. Especially the number of threads we could have on this, in this configuration is interesting for us, because even if we have actually less little cores than the big ones, as on the bottom line, we still have enough threads to dedicate a hardware thread to each component of our operating system. And I'm going to show you that the hardware threads that act as a container for the context of the process, and the hardware does the context switching on our behalf instead of us doing it in software, has some advantages later in this talk. So if we go back to the situation where we dedicated some of the cores and we're missing them somewhere else, and we replace them with small cores, suddenly it is much easier for us to take some of them and dedicate them to some of the important components of our operating system. We don't have such a hardware yet, though. So we take the existing hardware and we approximate. We have a dual socket quad-core Xeon configuration with 2 threads on each core. And we use frequency scaling to emulate slower in-order cores. Unfortunately, the frequency scaling on these chips only works in a fairly narrow range of frequencies. And we have to scale all the cores on a single die to the same speed. Luckily, the installed chips have also a feature called thermal throttling, which allows us to scale the chips further down and artificially emulate cores that are as slow as 200 megahertz, but it is just an approximation. We use the network stack to evaluate whether these really slow cores would give us any meaningful performance. We use a network stack because networking is a high-demanding application nowadays and stresses this part of the system a lot. Traditionally, in the multi-server systems, the network stack is a single component, usually accompanied by independent network drivers. We have broken up this single component into multiple small pieces for reliability reasons, which I'm not going to talk about here. And in our previous work, we have demonstrated that even such a network stack can still perform well. In the first scenario which we are evaluating, we use TCP streaming as a benchmark. We run the entire OS on one core, and we dedicate IP, driver, and the TCP components to their own cores. And we run the TCP clients on the remaining cores. So if you look at the performance we get only in the range of the frequency scaling, the red bar represents all 3 cores of the network stack which are stressed in this situation, running at a peak frequency of 2.2 gigahertz, while the blue bar shows all 3 cores running at 1600 megahertz only, and the green one is one of the middle frequencies. The first set of bars shows that as we decrease the frequency, the throughput, the TCP throughput, also drops. But it doesn't drop as quickly as the frequency drops, which is represented by the second set of the bars. What is more interesting is that the chip running at the peak frequency may draw as much as 80 watts, while if we scale the frequency down, we reduce the frequency, the peak frequency usage by 57%, while only degrading the TCP throughput by 9%. Well, so we at least save some energy while not decreasing the throughput significantly. But there are better configurations. If you run the TCP core at 1600 megahertz and the IP and driver on 600 megahertz both, we get a configuration which only uses 40% of the combined frequencies of the peak frequency, and we get a 5% improvement in throughput. We don't really know how much frequency, how much energy such a chip would draw if he really had such a chip, but it would be certainly less than 34 watts and probably significantly less. What we are really interested in is how the system behaves when the frequencies are very slow. The TCP component is the most demanding part of the stack, so it sort of determines the final throughput. The speed of the core sort of determines the final throughput of the stack. Here we have the configurations based on the TCP speed, and we always match it with the good configuration of the other two cores. In the first three sets, we use 200 megahertz for IP and driver. In the next two, we use 400 megahertz, and in the last three, 600 megahertz. 100% here is all cores running at a 2.2 gigahertz. If you look at the performance we get if we run all three cores at 200 megahertz only, we get a throughput of roughly 2 gigabits per second, which, in our opinion, is still pretty good for many applications. We can think of desktop computing or mobile computing. And as we increase the frequency of the cores, the throughput, of course, scales, and it looks like it scales linearly. But if we put in context the three other configurations which I showed previously, suddenly we have much faster cores, and we see a drop in performance, which if we put on the task faster cores, more energy, we can make up some of the performance loss, but not even all of it. We wouldn't see this dip only at the end of the graph, but we could see the same dip at every point in the graph if we scale the IP and the driver core to be too fast. So what's the problem here? As the components execute, the time goes from left to right, and execute the main loop and fetches jobs and work on the jobs, it comes a moment where there's a job arrives with a longer gap, and we poll for a while, but eventually the job arrives, we fetch the job, and we keep on processing. Everything runs smoothly, and everything runs in user space, and that's exactly what we want. Unfortunately, we don't really know how long should we poll, how hard should it be, and at some point we decide to sleep. We use the env instruction to monitor the activity on the job queues, but that's a privileged instruction on Intel chips. And once we decide to go to sleep, a job may just arrive. We realize it in the kernel, and we go back to the component that keeps working, but we've already introduced some latency. It's even worse when we actually block the CPU and we have to wake it up. It has even higher latency. So we're introducing this jitter, which TCP doesn't really like, and we introduce overhead by sleeping. It's not a problem if we use the CPUs close to 100% and we sleep rarely, or if the system is pretty much idle. But as the CPUs are utilized, say, in 30–40% range, we actually keep sleeping quite often, and we introduce quite a bit of chaos in the system, which degrades the performance significantly. So how can we solve it? Ideally, we would have the env instruction in user space, which is possible on some AMD chips. But nevertheless, there will be some latency in the sleeping involved. So the best is for us to use a resource which matches the needs of the component, which is as fast as we actually need and doesn't give us much opportunity to sleep and waste the cycles. Also, handling interrupts is a big problem, because the env instruction cannot really monitor two activities in the same time. So we can't monitor the device and the activity from the network stack at the same time. So we have to rely on interrupts. But handling the interrupt and waking up from interrupt has even higher overhead. In the second scenario, which we evaluate, we look at whether we can benefit from having multiple threads per core. The TCP is the most demanding component, so it runs on its own core, while IP and the driver have similar CPU usage, and therefore we put them on the same core, but different hyperthreads. In this graph, we compare the two scenarios. The green line is using 3 cores, and I've discussed it previously. The red line shows using 2 cores, one of them hyperthreaded. If we run the 2 cores at 200 megahertz, it gives us less throughput than using 3 cores at 200 megahertz. But the intuition is that if you run the core at the double of the speed of these IP and driver cores in the green case, we will get a similar performance. Actually, we get a better performance. And we get the better performance in quite a large range of frequencies. The reason is that the hyperthreading actually interleaves the execution quite efficiently, hides lots of memory latency. And in addition, if one of the threads is put on hold, the other threads may generate job, so we sleep even less. If you look at the point for 800 megahertz TCP core, you can see that we actually run the hyperthread core at 600 megahertz versus the 2 cores at 400 megahertz. And in all these cases, the CPU usage is smaller. Well, at some point, using 3 cores actually is better than using 2 cores, but that may be the effect of threading on out-of-order pipeline, and also we use significantly faster combination of the cores. Nevertheless, the difference is still not too big. So to conclude, we've proved that, or we've demonstrated that multi-server systems can perform well. We've done it in our previous work. Here we're showing that the slow cores can deliver good performance. And sometimes the performance is actually better than using significantly faster cores. And using the slower cores, the other benefit is that they likely use much less energy. However, the speed of the cores must really match the needs of the servers and the workload. And only heterogeneous cores can provide us with the right resources, because the CPUs can only run efficiently in a fairly narrow range of frequencies. So different cores would give us different ranges. Luckily, the heterogeneity we would like to exploit is becoming a reality. Companies are evaluating such products and actually start shipping these products. For us, what remains is to design the system that can adapt to the workload, that can, in runtime, evaluate the needs of the components and find a good placement. At the end, I would like to stress that performance is not everything, and in our design, we're focusing on performance, but we do not want to compromise on reliability. Thank you, and I would like to take your questions.
Hey, Scholt from ETH. Actually, what you were presenting, while you were presenting, I started to think if you think it would make sense to maybe manufacture CPUs which have, instead of just stepping the frequency down to, like 1,600 megahertz, actually could step it down in a few more steps. Do you think that would be a reasonable approach? Would that help kind of as an intermediate solution? So not to have like special CPUs with slow and small cores, but kind of have...
Well, I think that would help, but I don't think that it would save much energy. I think that's the biggest problem here. That's why you have the big little arm, where the little arms are much more efficient at the low energy, at the low frequencies energy-wise.
Hi, Anil from Qualcomm Research. My question is regarding the TCP experiments that you did. So a lot of modern hardware, networking hardware, and even in the software, there are things like interrupt mitigation. Like rather than generating 100 interrupts for 100 packets, you can configure the hardware to generate 1 interrupt. I'm curious if you're considering anything like that in your experiments.
Well, we do use an API approach. So when the driver really runs, it polls the device and only uses the interrupts when there's no work to do. Ideally, we would poll even when there is no work to do.
Okay. Another question I have is, you seem to be emulating some of the heterogeneous core with the frequency scaling, right? But if you really have some cores, you will have issues with cache coherency and transferring data overhead. How did you emulate those aspects?
Right, correct. We do lots of zero copying, so we only ship the control structures through the stack, not the data. And ideally, I would have finer-grained control over the cache. So I generate a message on one side, on one component, I want to ship it to the other side. That's something I don't really need to cache on the generating side. And similar effect. I think finer-grained control over cache would also help me, our system.
Hi, I'm Marius Hillenbrand from KIT. I was surprised to see the high latency in unblocking the CPU from an M RAID. Did you measure this delay?
It's an order of, I think, microseconds, tens of microseconds.
Thanks.
Also depends on whether you use some lower power state, which you can use with the M RAID.